Good afternoon, everyone. I heartily welcome you all to the 5-day faculty development program on algebraic structures organized by Research Department of Mathematics, Nesamani Memorial Christian College, Martanda. Now we are getting into first day of our program, so all the participants are requested to mute their mic. Now I invite Dr. A. Pramila Inbaros, Head of the Department of Mathematics, Nesamani Memorial Christian College, to deliver welcome address.
Honorable Speaker of the event, respected professors of our department, most respected participants of the program, a very good afternoon to you all. A warm welcome to the Faculty Development Program on Algebraic Structures from the Research Department of Mathematics, Nesamani Memorial Christian College, Marthandam. A very good personality and a dedicated leader with a strong determination is our correspondent, Professor Dr. AJS Praveen, who is a highly accomplished individual in the medical field. With great pleasure and gratitude, I extend a hearty welcome to our correspondent. A guiding light and a powerful motivation to all of us is our principal, Dr. R. Sheila Christie, who inspires us to work hard to raise our institution to greater heights. With a deep sense of gratitude, I extend a warm welcome to you, ma'am. An eminent, highly talented, well-experienced personality is our speaker, Dr. D. Kalamani, Professor, Department of Mathematics, Paradiyar University, PG Extension and Research Center, Erode. Ma'am has very deep knowledge in algebra, especially in lattice theory. Thank you, ma'am, for accepting our invitation. With immense pleasure and gratitude, I extend a hearty welcome to you, dear ma'am. A happy welcome to all the professors of our department. A warm welcome to the participants from all parts of our country. I invite you all to enjoy the session with concentration. Have a nice time. Thank you.
Thank you, ma'am. Now I invite Dr. T. Shaila Isaac Mary, Associate Professor, Department of Mathematics, Nesamani Memorial Christian College, to introduce our today's resource person. 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 To introduce our today's resource person.
Good afternoon, everyone. It's my honor to introduce Dr. T. Kalamani, a highly respected professor in the Department of Mathematics at Bharathiar University, PG Extension and Research Center, Erode. With 28 years of experience in teaching and research, she has made significant contributions to the fields of lattice theory, algebra, image processing, and graph theory. Dr. Kalamani holds MSc, MPhil, and PhD degrees and has made outstanding contributions to her field. She has published 50 research papers in international journals and 3 in national journals, presented 30 papers at international conferences, and written 2 books. She has also delivered 25 invited talks at various events. Dr. Kalamani has successfully guided 10 PhD scholars and is currently supervising 6 more. She has participated in 25 seminars and organized 20, which highlights her leadership and dedication to academic growth. Dr. Kalamani's work is an inspiration to students and colleagues. We are honored to have such a distinguished personality among us today in this online STP program. On behalf of the Department of Mathematics NMCC, I warmly welcome you, ma'am. And now hand over the session to Dr. Kalamani. And now hand over the session to Dr. Kalamani. And now hand over the session to Dr.
Hello, good afternoon to all. Hello, can you hear me? Hello, can you hear
Good
me?
afternoon, ma'am.
Is it a good afternoon, sir?
Good afternoon, ma'am.
Good afternoon to all. Good afternoon, sir. Myself, D. Kalamani, Professor and Head Department of Mathematics from Bharathiar University PG Center, Erode. Today, the afternoon is not the best time to teach mathematics, but we will make it best. First of all, I thank the correspondent. Dr. AJS Praveen, Dr. and head of principal in charge Sheila Christie, and head of the department Pramila Inpa Rose, and the convener Dr. D. Nita, for giving me the opportunity to present before the huge gathering. Thank you once again. Shall I now share the slides? Hello, ma'am.
Yes, ma'am, you are audible.
Okay.
Yes, ma'am, you are audible. Please share your screen, ma'am.
But somebody is requesting to join, so it's not opening, I think. Sharing screen.
Yeah, okay, ma'am. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present. We will take care of it. That's not a problem, ma'am. You can present.
So the screen share option is not opening because of the request. 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 Not opening because of the request.
Ma'am, you can try now.
Yeah.
Ma'am, you can try now.
Yeah.
Ma'am, you can try now.
Yeah. Can you see the screen now? Can you see the screen now?
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Okay. Once again, good afternoon to all. Okay. Once again, good afternoon to all. Once again, good afternoon to all. My presentation is on the topic S prime ideal as S meet semilattice. First, we are giving the those who are familiar or unfamiliar. We start with the introduction from the part algebra ring theory, and then from lattice, and then we we see some properties of S prime ideal, and then some properties of S meet semilattice, and then we see how S prime ideal is S meet semilattice. So in the introduction part, first we will see what is a ring theory. Ring is a non-empty set with two operations, addition and multiplication. Under addition, it should be an abelian group, and it satisfies closure property and associative under the operation multiplication. And the operation should be distributive, that is addition over multiplication and multiplication over addition. And some of the examples are set of integer is a ring under addition and multiplication, and some more are set of rational numbers, set of real numbers, complex numbers. And these set of rational number, real number, complex number are fields also. That is, it satisfies under multiplication, it is an abelian group, and it satisfies distributive property. But Z is not a ring, sorry, not a field, but only it is a ring because it does not have a multiplicative inverse. And the set of integer modulo n is a ring, not a field. ZP, when it is prime, P is a prime, it is a field. And we'll see some the definition of a subgroup. A subgroup is we can take any subset of a ring. That subset should satisfy subgroup of R, and it should satisfy the closure property. It should be closed under multiplication. Then it will be a subring. And also, if it is just a non-empty subset of R, and if it satisfy closure property and after multiplication, again you can say the subset S is a subring of R. Then a set of even number is a subring of Z, set of integers, and Z is a subring of Q is a subring of R, and you can say Z is a subring of R itself. Now, but Zn is not a subgroup. Why it is not a subgroup is under Zn we are using the addition as addition modulo n, but in Z we are using the ordinary addition. To be a subring of ring, it should both the operation must be the same. So these two operations are different. So Zn is not a subgroup of Z. Next, we will see the definition of an ideal. Ideal is a subring of R. It should satisfy two conditions. It should be subring of R, and it should be closed under multiplication with all the elements of R. That is, if you take any element from I and any element from R, when you multiply, that must be in I. And it should be a subring. It is called an ideal. Suppose if R is multiplied, if A is an element of if A is an element of I and R is an element of R, If RA is in I, the ideal is called the left ideal. If AR belongs to I, then the ideal is said to be right ideal. If it is both left and right ideal, it is called the ideal. Some of the examples are if you take integer modulo 12, it contains 12 elements 0 to 11. The ideals are the generators are the devices of 12. The ideals generated by 1, 2, 3, 4, 6, 12 are the devices of 12. If it generates any ideal, if it generates any set, it is an ideal. It satisfies the ideal property conditions. Some of the types of ideal: prime ideal, maximal ideal. Prime ideal is if you take any two elements in R, A comma B is any two elements of R, and if the product is in the ideal, then one of the elements should be in the ideal. Either A is in the ideal P or B is in the ideal P. Then the ideal P is called the prime ideal. That is, if any ideal, if it is generated by the prime elements of integer modulo n, they are the prime ideals. Ideal generated by 2, in Z12, ideal generated by 2, ideal generated by 3 are the prime ideals. And the next one is the maximal ideal. Maximal ideal is the it is the proper ideal. There is no other ideal which contains M. It is the maximal one. If you consider either, if any ideal contains M, then it is either equal to M or it is equal to R. Any maximal ideal, the relation connecting prime and maximal ideals are any prime ideal, maximal ideal is a prime ideal, but prime ideal need not be the maximal ideal. Only in Zn, that is in finite commutative ring, prime ideal and maximal ideals are the same. In general, it is not true. And next, we will see the definition of the multiplicative set. What is multiplicative set is it is a subset of the ring, and if you take any two elements in the subset, the product should be closed. It is closed under multiplication. And in if you take a prime ideal, if you take the complement, it will be the multiplicative closed set. And if you collect set of units, units means that is the set of elements which are having the multiplicative inverse. So if you collect the set of units from the ring, it will form a multiplicative closed set. In the same way, if you collect the zero devices are if you take any element in R, if there exists an element B such that A into B is 0, they are zero devices. If you collect the set of zero devices of Zn, it will form a multiplicative closed set. Next, we will see what is S prime ideal. S prime ideal is the generalization of the prime ideal. In prime ideal, if AB belongs to I, then either A belongs to I or B belongs to I. But in S prime ideal is the proper ideal of R, and it is the disjoint from the multiplicative set. S intersection I is equal to null set. And if AB belongs to I, then SA belongs to I or SB belongs to I. For some S in S, if there exists an S in S such that SA belongs to I or SB belongs to I, we call the proper ideal I as the S prime ideal. Example in Z6, the ideals generated by 2, 3, and 6 are the S prime ideals. How to find the S prime ideal is you can write the devices of n, and those are the ideals. The ideals generated by the devices of n are the ideals. And in that, the devices, if you write as the prime factorization, if it if the prime power is, if at least one of the prime power is 1, it will be an ideal. Otherwise, it is a non-prime ideal. In 6, the devices are In Z6, the devices are 1, 2, 3, and 6. These are the devices. So, 4 ideals will be formed. In that 2, when you are writing a prime factorization, the power is 1, 2, 3. Always the prime ideal is an S prime ideal. So, ideal generated by 2 and 3 are S prime ideal. In 6, you can write it as 2 into 3. So, the power of 2 is 1, power of 3 is also 1. If at least one prime has the prime power as 1, then it is an S prime ideal. Uh, so you always prime ideal is S prime, but S prime ideal need not be prime. So it is S prime is prime only when if S contains units. S contains a unit or zero devices. If it contains a unit, then S prime ideal is same as the prime ideal. These are the some examples given for some Zn for some of the values of n. You can see for n equal to 24, the devices are, you can take n equal to 12. We take simple example. The devices are for 12, 1, 2, 3, 4, 6, 12 are the devices. Here when you take the ideal generated by 1, it will give the whole ring. So it is not a proper ideal, so it is not the S prime ideal. Ideal generated by 2 and 3 are prime ideals, they are S prime ideals. Ideal generated by 4 is equal to 2 square. No prime having S in power 1. So it is not the ideal generated by 4 is not the S prime ideal. Ideal generated by 6, ideal generated by 12. 12 is 2 square into 3. Power of 3 is 1. So ideal generated by 12 is an S prime ideal. In the same way, you can find the S prime ideals for any value of n. Here some of the examples are given. So far we have seen the basic concepts of ring theory. Now we will pass on to the next domain, that is the lattice. In a lattice, first we will see what is a poset. Poset means it is a partially ordered set. It is a set which has relation, some relation. We are denoting as a less than or equal to. Less than or equal to not the original meaning. It means it is a relation. It may be any relation, divides relation or subset relation. It may contain any relation. So any set together with the relation satisfies the reflexive, antisymmetric and transitive property, then the set is called the partially ordered set. I think you know what is reflexive. Reflexive means any element related to itself. Suppose if you take an element divides relation, 2 divides 2. So every element is related to itself. Suppose if you take subset relation, A is a subset of B. So it is a reflexive property. Antisymmetric is if A is related to B and B related to C, then A equal to, sorry, not C, A related to B and B related to A, then A equal to B. That is under subset relation, A subset of B, B subset of A means A equal to B. So subset relation is an antisymmetric relation. Similarly, transitive relation is A subset of B, B subset of C, then A is a subset of C, a transitive relation. So if the relation satisfies these three properties, then it is called the poset. An example is given, that is P equal to 1, 2, 3, 4, 6, 12. That is the devices of 12. And the relation divides. So divides relation is reflexive, that we know. Any element divides itself. And then antisymmetric is if A divides B and B divides A, then A is automatically equal to B. And similarly, if A divides B, B divides C. 2 divides 4, 4 divides 8, then 2 divides 8. That is possible under divides relation. So therefore, divides relation is partially ordered relation, and the set together with the partially ordered relation is called the partially ordered set. And we can represent this partially ordered set as a Hasse diagram. In a Hasse diagram, always if any element A is less than or equal to B, we can connect it by taking the element joined by a line. By taking the line, if A is less than or equal to B on the top, A in the bottom. Suppose A less than or equal to B less than or equal to C, by transitive property A less than or equal to C. So you can just denote A to B and B to C. No need to represent a line for A to C. You can avoid it. That is automatically true. It is denoted in the next slide. So this is two divide 6. You can represent in a graphical representation. This is a Hasse diagram for the given P. And the top elements are maximal elements and the bottom elements are called the minimal elements. In a poset, maximal and minimal elements need not be unique. Next, we can define lattice. What is a lattice? It is a first. It should be the poset, and it contains. You have to find for any two elements, meet and join must exist. That is, if you take any two elements, you can find the lower bound. Lower bound means it may contain more lower bounds. That is, for 6, the lower bounds are 2, 3, 1. And greatest lower bound is that is 6 only. For 2 and 6, if you take any two elements 2 and 6, the lower bounds are 1, 3, 2, 1, 3. So for 2 and 6, 2 is the lower bound, greatest lower bound. Similarly, you can find the upper bounds. For upper bounds of 2 and 6 are 4, 12, 2, 6 all upper bounds. Here the least one is for 2 and 6 is that is 2. So for any two elements, if the greatest meet and join exists, that is denoted by meet, that is the symbol here given. Join exists for any two elements, it is a lattice. And in a lattice, maximal element and minimal element should be unique. So next we will see meet semilattice. Semilattice is it is a meet semilattice or a join semilattice. In a meet semilattice, for any two elements, the meet should exist. More than one maximal element exists, but minimal element should be unique. In a joint semilattice, for any two elements, a join must exist. Meet more than one minimal elements may exist in a joint semilattice. So in the previous example, if you consider L equal to 1, 2, 3, 4, the relation divides, it is a meet semilattice. So if you consider only 1, 2, 3, 4, only these four elements, here 3 and 4 will not have the upper bound. Only meet will exist. So meet is unique. That is, sorry, the minimal element is unique. Maximal element, two maximal elements, 3 and 4. So it is a meet semilattice. Similarly, you can take the, suppose 4, 6, 12, two minimal elements, only one maximal element. It is a joint semilattice. So in a meet semilattice, minimal element is unique. More than one maximal element will exist. In a joint semilattice, maximal element is unique, more than one minimal element exists. The two examples are given for the above Hasse diagram. So next we will see, already we have seen what is S prime ideal. Here we will see some properties of S prime ideal. Now we can define a set I over S. I over S is set of all x in R such that Sx belongs to I for any S belongs to be an ideal of R. Can you all understand? Do you all follow? Can you hear me?
Yes, ma'am.
Okay, thank you. Here the set I over S is set of all x in R such that Sx belongs to I. It is an ideal. How it is an ideal is to prove an ideal, you have to take an element from the set. You can take A belongs to I over S. If A belongs to I over S, it means Sx is SA is an element of I. Now you can consider any element R from R, and you have to prove RA or AR belongs to I over S. That is to prove RA belongs to I over S. To prove RA belongs to I over S, already we know SA belongs to I. SA belongs to I means I is an ideal. So RSA belongs to RSA belongs to I. So RSA belongs to I means RA belongs to I. Sorry, RA belongs to I over S. Therefore, I over S. Similarly, you can prove AR belongs to I over S. Therefore, I over S is an ideal of R. And an important property is the ideal I is S prime if and only if I over S is a prime ideal. For some S in S, if there exists an S in S such that I over S is prime, then you can I is S prime ideal. And also if you take the intersection of all the prime ideals, it will give you the nil radical. Nil radical means it is the collection of all nilpotent elements. Then what is nilpotent element? Nilpotent element is an element is called the nilpotent if its power sum for any power it is 0. If A is a nilpotent, A power n for some n integer, it is 0. So the intersection of all prime ideals is a nil radical of or collection of all nilpotent elements. This will give you the S prime ideal. All prime ideals are S prime ideals, and the intersection of all prime ideals will be the non-prime S prime ideal. And if you take the ring is of order p power t into q power t, it is 2 square into 3 square like that, then the non-prime S prime ideals are nilpotent ideals. Nilpotent ideals means an ideal is said to be nilpotent if you take any non-prime S prime ideal, if I is a non-prime S prime ideal, it is called the nilpotent if I power n equal to 0 for some n for some integer n. But it contains some nilpotent elements, not all, need not be all nilpotent elements, it is some nilpotent elements. For example, in Z36, if you take the S prime ideals are, already we said If it's one of the prime contains the devices, prime factorization contains power is 1. It is an S prime ideal. So ideal generated by, you can collect the devices of 36 and collect the ideals generators prime factorization contains one of the prime power is 1. So the ideals are 2, 3, 6 is 2 into 3, 2 square is 3, 18 is 2 into 3 square. So these are the S prime ideals. In we know that in Z36 nilpotent elements are 6, 12, 18, 24, 30. That is here in S prime ideals, non-prime S prime ideals are 6. Non-prime S prime ideals are 6. It contains the elements 0, 6, 12, 18, 18, 24. These are the elements of ideal generated by 6. This is a non-prime ideal. Here it contains 30 also, all the nilpotent elements. If you take the non-prime ideal 12, it contains the elements 0, 12, 24. The 36 is 0. So it contains all the nilpotent elements. Similarly for 18, 0 and 18. So the non-prime S prime ideas contains nilpotent elements. Is it 36? 36 can be written as 2 square into 3 square. That is in the form P power T into Q power T. So it will satisfy the condition non-prime S prime ideal is a nilpotent ideal. Next, so far we have seen the S prime ideal, some properties of the S prime ideal. So if any ring is given, you can collect the S prime ideals and you take the all the S prime ideals as a set. That set is denoted as LS. LS is the collection of all S prime ideals. And in that, if you use the relation, subset relation, LS subset, it is a poset. It satisfies the all the properties of the partially ordered relation. And this need not be a Smith semilattice. If to be an Smith semilattice, every pair of elements must have the meet, and to be the joint similattice, every pair of elements should have the joint. It is denoted by, if it is meet similattice, LS meet. If it is joint similattice, it is denoted as LS joint. But all the collection need not be meet similattice or joint similattice. For example, you can take say integer modulo 12. Here the S prime ideals are, you can take the devices and then you can find the S prime ideals of Z72. The S prime ideals are ideals generated by 2, 3, 6, 12, 18 and 24. Collect those as a set. LS is the collection of all the S prime ideals. It is a post. It is represented in a Hasse diagram. From the Hasse diagram, you can say directly whether it is a lattice or not. We know in a lattice, every pair of elements should have the meet, and every pair of element to have the join. But for 24 and 18, no meet, and 2 and 3, no join. So two maximal elements. In a lattice, maximal element is unique, minimal element is unique. Here two maximal elements 2 and 3, minimal elements 18 and 24. It is not a meet similattice or joint similattice. But if it is of order p power t or p power t into q or p power t into qr and p power t into q power s into r, where p, q, r are distinct primes, then they will form a S-meet semilattice. But 72 is not in this list, so it is not a S-meet or S-joint semilattice. So here the general Hasse diagram is given for all the powers for p power t and here p power tq. Here you can say the minimal element is unique, maximal element, two maximal elements, so it is a meet semilattice. Here this is the Hasse diagram for p power t into q into r, where p, q are primes. The minimal element is unique and the maximal, there are three maximal elements. So it is a meet semilattice. It is the Hasse diagram for t into q power s into r. Here the minimal element is unique, maximal element, three maximal elements. So it is meet semilattice. So because it is a collection of all S prime ideas, we are calling it as S meet semilattice. Some properties of S meet semilattice. Here if you take any chain of LS, chain means if any two elements in the Hasse diagram must they are comparable. So you can consider the maximal chain. In the maximal chain, it has exactly only one prime ideal. For example, here you can take the maximal chain 3, 6, 12, 24. That is any two elements are comparable. Similarly, 2, 6, 18, that is a chain. In the maximal chain, if you take, it contains only one prime ideal. And if you can consider the number of maximal chain is not equal to number of prime ideals, but number of maximal chain is greater than or equal to number of prime ideals. So they are equal only if the power is of, if the ring is of order p power t into q form. If p is the prime ideal of R, it is the maximal element of the poset. If it is a prime ideal, it is the maximal element for the poset. Here the example definition of a downset is given. The same Hasse diagram is given. So downset means you can collect D as the subset of LS, and you can take any element in the subset and any other element in LS, any element in LS. And if the element B is a subset of A, that is B is related to A, then the element B will be in D. If it's so, then the set D is called the downset. It is denoted as downset of D. Here, for example, if you take the element 2, downset of the ideal generated by 2 is 2, 6, 12, 24, 18, these elements. Downset of 12 is 12 and 24. Downset of 6 is 6 and 18. Sorry, downset of 6 is 6, 18, 12, 24. All these elements are downset of 2. We have seen what is the ideal of a ring. Here we define the ideal of the S-meet semilattice. There we have defined ideal of a ring is an element A from I and R from R. Then RA and AR must belongs to I. Then it is called the ideal. Here it is a meet. We are finding the ideals of the S-meet semilattice. I is must be the there I must be the subring. Here I must be the sub semilattice, sub S-meet semilattice. And if you take any element in I and A belongs to LS, then I meet A belongs to Y. This is like there we have defined left ideal, right ideal. Here I meet A belongs to I means it is a ideal of the meet semilattice. If I join A belongs to I, it is a joint similatris, ideal of the joint similatris. Here we are defining the ideal of the meet similatris. Always 0 and LS are LS. Same as we defined in a ring, we can define an ideal, a prime ideal for S meet similatris. I is prime if and only if AB belongs to LS and A meet B belongs to I, then either A belongs to I or B belongs to I. Then the ideal is said to be prime ideal. Similarly, as we defined maximal ideal in a ring, you can define a maximal ideal in a S-meet similatris. That is, if you take I is a maximal ideal, and the only ideals containing I are I and LS. That is there is no other ideal which contains I. It is the maximal one. Wait a minute. So far we have seen part of the ring and lattice, and then properties of we have defined what is S prime ideal and what is S meet similatris, and some properties of S prime ideal and S meet similatris are. Next we will see some concepts in results in S meet similatris. So first one is we are seeing the generalization of an S prime ideal. You can take any S prime ideal and you can generalize and find how many S prime ideals are in LS. LS is the collection of S prime ideals. Here how many S prime ideals are in LS. That is how many elements are in LS. That is cardinality of LS we are seeing. If R is a ring of order n, then n equal to p1 power alpha 1, p2 power alpha 2, etc., pk power alpha k. These are distinct primes and alpha is greater than or equal to 1. Then the cardinality, that is the number of S prime ideas, is tau of n minus product of alpha I. Tau of n is the number of devices of n. So if any number n is given, to find the devices, suppose if n equal to 6, where will you find the number of devices? Number of devices is you can write in a prime factorization method, that is 2 into 3. Tau of n equal to, that is p1 power alpha 1, p2 power alpha 2, alpha 1 plus 1 into alpha 2 plus 1. That is 1 plus 1 into 1 plus 1. That is 4. That is 1, 2, 3, 6 are the devices of 6. In the same way, you can write the, suppose if you take 72, if you take 72, it can be written as 72 is 2 cube into 3 square. The number of devices 3 plus 1 into 2 plus 1. That is 4 into 3, 12 devices. So tau of n, you can calculate tau of n minus product of alpha I. Alpha is powers. Alpha 1, alpha 2 into alpha 3, etc. Pardon, ma'am? Excuse me. So to find the number of prime ideals, number of S prime ideals, first you are taking IS dash as the non-S prime ideal. And if you take the whole set R is a ideal, but it is not the S prime ideals. If you consider R is also the whole ring R is an ideal, but it is not the S prime ideals. So it is generated by the divisor 1. So it is not an S prime ideal. S prime ideal is a proper ideal. So number of S prime ideal is less than tau of n. It is not equal to tau of n. It is less than tau of n. And any ideal of R is a divisor. So you can take the I as the ideal generated by P1 power beta 1, P2 power beta 2, P3 power beta 3, etc., Pk power beta k. Suppose you have in 72, it is 2 square, 2 cube into 3 square into 3 square. The devices are 1, 2, 3, 4 into 3, etc. like that. That is the powers varies from 0 to 3 for first prime 2, and for second prime power varies from 0 to 2. So these are the devices. Suppose if you take 2 power 0, 3 square is a divisor, 3 power 0, 1 is a divisor, 3 is a divisor. When 3 equal to 1, 3 equal to 9 is a divisor. So the power varies from 0 to 3 for the prime 3, 0 to 2. So I equal to ideal generated by P1 power beta 1, etc., Pk power beta k. The power varies from 0 to alpha I. So these are the beta. For beta I varies from 0 to alpha I are the devices of R. So the ideal generated by these devices are the ideal I. And you can take the complement of primes, ideal generated by P1, ideal generated by P2, etc. So ideal generated by P1 you are getting by taking beta 1 equal to 1, the other beta is equal to 0. Similarly, you can get the ideals, prime ideals. So if you take the complement and we are denoting this as S1, S2, etc., Sk. And these will be a multiplicative closed subset. It will satisfy the closure property under multiplication. So these are the multiplicative closed subset which will be disjoint from I. And to collect the non-prime S prime ideals, first we are taking, suppose already we know if any one of the power is 1, we will get the S prime ideal. So first we are considering all beta I not equal to 1. Then we should get the ideal is a non-prime S prime ideal. Sorry, non-S prime ideal. So we are considering beta I not equal to 1 for all I. And if it is any non-prime ideal, and if I over S is prime, to be a non-S prime ideal, I over S is non-prime. Suppose if it is a prime, we are assuming that if it is a prime ideal, then you can consider it is given as S over I. It should be written as I over S. I over S is ideal generated by P1 or ideal generated by P2, etc. Prime ideal. So here we are assuming that it is ideal generated by P1. Here P1 is not equal to 0. So you consider an element S as P1 power beta 1 minus 1, etc. Pk power beta k. This element will be an element of all the prime ideals. So it because it contains the prime elements, it is an element of all the prime ideals. So that means it is an element of the nil radical. So it is a nilpotent element. If it is a nilpotent element, it is not an element of S. Nilpotent elements means it is a element of the ideal, but multiplicative set are disjoint from I. So it is not an element of S. So it is a contradiction. So I over S is not a prime. So if I over S is not a prime, I is not an S prime ideal. So when beta I not equal to 1 for all I, we are not getting I as S prime ideal. So next we are considering beta I equal to 1. If beta I equal to 1 for some I, for not no need for all I, if some I beta I equal to 1, we will get the S prime ideal. So if let it be beta 1 equal to 1 and consider the ideal as beta 1 is 1, so ideal generated by P1, P2 power beta 2, etc., Pk power beta k. So this beta I value 2 to k varies from 0 to alpha I. So if you consider any element, there exists an element from S1, it will form I over S will become ideal generated by P1 you will get. There exists some element in S1. So this ideal will be, it is a prime ideal, so the ideal I will be an S prime ideal. So when beta I equal to 1 for some I, we get an S prime ideal. And we have to collect all those S prime ideals. We have to count it. So the number of, we have to first find number of non-S prime ideals. So R is not an S prime ideal. It is a whole ring. S prime is proper ideal. It is not a S prime ideal. Then any ideal generated by P1 power beta 1. So here we have beta I is not equal to 1. So ideal generated by P1 power beta 1 is not a S prime ideal. Similarly, P2 power beta 2, etc., Pk power beta k. The combination of 2 primes, combination of 3 primes, etc., combination of S primes. The power is for all I not equal to 1. So you can count all this for R one ideal 1 for ideal generated by P1 power beta 1 except for beta 1 equal to 1 all the ideals are non S prime ideals. So we have alpha 1 minus 1. So beta 1 varies from 0 to alpha 1. For beta 1 when you subtract alpha 1 minus 1. Similarly, for ideal generated by B2 power beta 2, alpha 2 minus 2, alpha 2 minus 1, etc. In the same way, for 2 primes, alpha 1 minus 1 into alpha 2 minus 1, etc. When you simplify all this, expand and simplify, you will get the number of non-S prime ideal is the product of the primes, alpha 1, alpha 2, etc., alpha k. So number of S prime ideals equal to number of ideals of R minus number of non-S prime ideals of R. The number of ideals is number of devices that is denoted by tau of n. minus number of non-S prime ideals, product of alpha I. So tau of n minus product of alpha I will give you the number of S prime ideals of R or the cardinality of LS. So this is an example for this one. Is it 180? When in 180, you can expand it 2 square into 3 square into 5. Tau of n you can multiply 2 plus 1 into 2 plus 1 into 1. That is 3 into 3 into 2. Sorry, 1 plus 1. 2. You will get 3 into 3, 9 into 2, 18 number of devices. So 18 ideals we have. And S prime, non-S prime ideals are the ring R and 2 square, 3 square, 2 square into 3 square are non-S prime ideals. There are 4 non-S prime ideals, and then the other are S prime ideals. Tau of n minus product of powers is 18 minus product power is 2 into 2 into 1, 18 minus 4, we have 14 S prime ideals. So for this, the Hasse diagram is given. And the next one is, already we have seen what is a downset. So here I is the subset of S-mid semilattice. Then the ideal, the subset I is an ideal if and only if I can be written as the union of downsets. If it is a trivial ideal, it is the downset of the minimal element. That is the last element, bottom element, bottommost element. And otherwise, if it is non-trivial, you can write it as it is the union of T downsets of element, downsets of some element. The elements are from LS. Here the proof is given by collecting the elements. For I is trivial and for I is non-trivial. That is for if I equal to D1, it is an ideal. Similarly, I equal to D1 union D2, it is an ideal. Union D3, it is an ideal. Up to, you can write the union of downsets of elements, union up to etc. dt. T varies from 0 to r minus 1. 0 to r minus 1 is number of elements in LS. Suppose if there are r S prime ideals, it is up to r minus 1. If you take all the elements instead of r minus 1, if you take r, d1 union d2 union etc. union dr, this will give you, what is this I? Instead of taking r minus 1, if you take r, what is the union of downsets of all the elements of LS? What is this I? Can anyone say? My talk is understandable or online class is very difficult to understand, but can anyone say I is equal to what? Why we are considering I up to r minus 1? If you take up to R, you are taking all the downsets. If you take the downsets of all the elements, then the union of all the elements will be, suppose you take the top element. The top element is any element. It is a poset, no need of it is a Smith semilattice. It may have more than one maximal element. Suppose 2 and 3 are the maximal elements. Suppose when you consider the down set of 2, 3, then what will be I? If A is related to B, downset of B is same, downset of A is contained in downset of B. That is true. Then what is I? If you consider the all the downset of all the elements, it will give the total ring. It is not proper. So you should not consider all the elements. So you have to consider only up to R minus 1 elements. Union of the downsets of R minus up to R minus 1. You can take a single downset at D1. It is an ideal. Two downsets D1 union D2. It is an ideal. Up to dr minus 1, it is an ideal. So the proof is given here. Next we have seen these are the relation between the ideal and downsets. So the first one is ideal if and only I is the union of downsets of the elements of LS. Next, if you take the I as the union of downsets of only the maximal elements of LS, then it will give you the prime ideal. So I is the prime ideal if and only if I is the union of T downsets of the maximal elements. Here these are the proof given. The next one is in the same way, if it is a maximal ideal, if and only if I is the union of K minus 1 downsets of Mi. So what is the difference between the prime ideal and this one is, that is the union of T downsets. T varies from 0 to the maximal elements. Suppose if you have 3 maximal elements up to 2. But here you are having a union of K minus 1 downsets. If I equal to, suppose if A and B are the maximal elements, dA, it is the downset of dA, it is the prime ideal. Then dB, I equal to dB is the prime ideal. I equal to dA union dB is the prime ideal. Here in that the maximal ideal is dA union dB. So only this one is the maximal ideal. So it contains only union of K minus downsets of the maximal. Mi is the maximal element of LS. So up to, you can take if there are K maximal elements, you have to consider any K minus 1 downsets of but also the prime ideal. You can take the single double union, 3 elements, 3 down. This is the proof given. And every maximal ideal is a prime ideal, but prime ideal need not be the maximal ideal. It is true when the ring is of order p power t into q. So here we have considered an example. R is Z30. It is integer modulo 30. Here the S prime ideals are 2, 3, 5, 6, 10, 15, 30. Here the ideals are, there are 18 ideals. It is the acid diagram for it. There are 18 ideals for Z30. This is the one. Sets of generated by 2. From the previous one, ideal generated by 2, that is the downset of ideal generated by 2 is 2, 6, 10, 30. These are the elements. Downset of 3, 3, 6, 15, 30. Similarly for 5. And also you can find the downset of 2 union 3, etc. 2 union 3 is the elements of downset of 2 and the elements of downset of 3 will be in downset of 2 union 3. So first one, ideal generated by downset of 2, downset of 3, downset of 5. Next one, ideal generated by 6. Ideal generated by 6 is 6 and 30. Ideal generated by 10, 10 and 30. 15, 15 and 30. Like that the elements are given. For ideal generated by the minimal element, only the corresponding element will be in there. Then the ideal generated by the two sets, ideal downset of D1, downset of D2, two unions. Suppose if you find downset of 2 and downset of 6, you will get only downset of 2. That is, downset of 6 is contained in downset of 2. So when you find the union of these two, you will get only downset of 2. So similarly, downset of 3 union downset of 15 is downset of 15. So using the property, we are finding the union of two ideals, two S prime ideals, and then three S prime ideals. If you set of all the prime ideals, you get the total collection LS. So there are 18 S prime ideals, 18 ideals for S meet semilattice, and these are the three are the prime ideals, and these three are the ideal generated by 2 union 3. So prime and maximal ideal. So here we have three maximal elements, prime elements. So here we are taking only 2 elements for the maximal ideal. This is the collection of union of downsets of maximal elements. T varies from 1 and 2. So these are the we are used. And this paper, the properties on S prime ideal as nilpotent ideal is published in Journal of Applied Mathematics and Informatics. And this S prime ideal as S meet semilattice published in AEM. We have drawn the graph also for the S meet semilattice and some other research papers. If you have any queries, if you want, I will explain the theorem, but the time is almost 3:15. Uh,
Thank you, ma'am. Thank you for your presentation.
okay.
Nice. Thank you for your nice
Okay, ma'am.
presentation, ma'am. Now the participants can ask the questions. If you have any doubt, ma'am will clear you. There are some questions are posted in YouTube comments.
YouTube comments, okay.
Yeah, ma'am. I will read. Can you please explain the relationship between semigroup and lattice?
Semigroup, it is under the domain ring, the elements from the ring are group elements. Lattice is another domain.
Yeah, ma'am. Another question is the structure lattice. Is the structure lattice a generalization of the structure ring? Is the
Which one,
structure
ma'am?
lattice a generalization of a structure
Yeah.
ring?
Yeah.
Yeah, one more, ma'am. Shall we define homomorphism, isomorphism in semilattices?
Between two semilattices. Are you asking between two semilattices?
Yes, ma'am. Yes, ma'am.
Okay, we can define homomorphism using the meet and join operator. Semilattice means if you have only one meet, you can define f of a meet b equal to f of a meet f of b. You can define the homomorphism.
Okay, ma'am. So participants in meet can ask your questions now. Participants? Shall okay, ma'am. I think no one have questions. So this is the end
Okay.
of our session. Thank you so much, ma'am.
Okay, thank you.
Questions posted in YouTube.
This is our end of our session. Now I invite Dr. D. Nida, Assistant Professor, Research Department of Mathematics, Nesamani Memorial Christian College, to deliver vote of thanks for today's program.
Thank you, Ashika. First, I would like to express our heartfelt gratitude to Dr. D. Kalamani ma'am for insightful and thought-provoking session. Your expertise and passion on S prime ideal as S meet semilattice has truly enriched our understanding and inspired us all. Next, I thank our HOD, Dr. A. Pramila Inbaros, whose dedication and hard work made this event successful. Next, I would like to thank all the staff members of our department for their constant support and their encouragement. Finally, a warm thank you to the technical team of our resource scholars for ensuring everything runs smoothly. Thank you once again for being a part of the session. Thank you. Thank you all.
Participants are asked to fill the feedback of today's session. Thank you. We can meet on next session.
Shall I left, ma'am?
Yes, ma'am. You can leave now. Thank you, ma'am.